we finally made it to the last chapter of the course. So we have just about another week or so left to go, and we're going to end here with a discussion of thermochemistry. And we're going to make connections all the way back to the first chapter. Remember back in chapter 1 we were looking at the potential energy, that's the stored energy associated with electrons in atoms and then eventually molecules. And let's just recap for a minute. When we put an electron into an orbit, is that energy absorbed or released? Well, that energy is released. We have this favorable attractive force between the nucleus and the electron, and energy is released. We reach a low energy potential. Okay, now as we extend that to chemical bonding, what happens when we form a chemical bond? Is energy absorbed or released? Well, energy has to be released. Otherwise, there would be no driving force. There would be no energetic reason for a chemical bond to form. So we reach a lower energy configuration when we have a chemical bond, and that energy is then released. In this unit, we're going to look deeper at the potential energy in chemical bonding. Let's take a look at this seemingly simple reaction. Hydrogen gas reacting with oxygen gas. You can test yourself, but this hopefully you have seen a few times by now. Produces water. This is a type of combustion and combination reaction. So if we balance this, we have 2, 2, and 2, and we can measure the delta H. That's the heat given off for this combustion reaction, and it's negative 483.6 kilojoules. And what does this mean? Kilojoules, what? It's kilojoules of heat per 2 moles of hydrogen that were combusted. And so this is actually kilojoules per X moles of reactant or product. So we can write this several different ways. 483.6 kilojoules per 2 moles of hydrogen. We could write it as negative 483.6 kilojoules given off per 1 mole of oxygen, or we could write it as negative 483.6 kilojoules given off per 2 moles of water produced. And essentially what this is, this heat, will end up being a conversion factor for us. So if we want to use 10 moles of hydrogen, we would be able to use this conversion factor here to determine how much heat would be given off for 10 moles of hydrogen, essentially doing a unit conversion. But we want to take a step back and say, well, let's look at this in terms of the chemical bonds. So we are breaking 2 HH bonds here, and we are breaking 1 oxygen double bond. So we could call, okay, we're breaking 1 sigma and 1 pi here, and in this case we're breaking 2 sigmas. So we have 3 sigma bonds and 1 pi bond that are being broken. All right, and we know that we have to put energy in to break bonds, right? But energy is coming out of this, okay? So that means the bonds that we form, what bonds are we forming? We're forming 4 oxygen, hydrogen single bonds. And these are all sigma bonds. 4 sigma bonds formed. Well, these bonds that are formed, right, are releasing energy. And the energy released when these are formed must be greater than the energy needed to break these, hence the energy released. So the bonds that we formed are stronger than what was broken because energy was released here. Okay? So think about bonding in terms of those thermodynamics. Stronger versus weaker, right? So the same number of bonds, 4 and 4, were broken and formed, but look at what kind, right? 4 sigma versus just 3 sigma and 1 pi. Think back to the bonding chapter, what was it, 9, I think it was, where we talked about pi bonds, and pi bonds are a weaker bond. That second bond in a double, or the second and third bonds in triple bond systems, are weaker. That side-to-side orbital overlap of those p orbitals is a weaker, poorer interaction than the end-on-end overlap of the sigma bond. We just took a look at that combustion reaction of hydrogen and oxygen to make water, and that was an example of a thermochemical equation. And a thermochemical equation is a balanced chemical equation that includes the heat of the reaction. So having that delta H value makes that a thermochemical equation. Let's look at another example. Take, for example, the combustion of methane. We'll produce carbon dioxide and water. Let's not forget my phases here. And this reaction has a delta H, sometimes you'll see subscript reaction, RXN, of negative 802.3 kilojoules. So there is a thermochemical equation, right? And we will be able to look at this thermochemical equation and determine this value both experimentally through calorimetry and then also approximating it using various pieces of data like heats of formation, bond dissociation energies, or even Hess's law where we have other known reaction enthalpies. Okay? So because these are enthalpies, let's review some characteristics of enthalpy. There are three characteristics of enthalpy that will be useful for us to consider. Enthalpy is an extrinsic property. And if you forget what extrinsic property is, it's a property that depends on the amount. Okay? So if I have 1 mole of hydrogen versus 2 moles of hydrogen, a different amount of heat is going to be released, highlighting the fact that enthalpy is an extrinsic property. The opposite of extrinsic, as you might recall, is intrinsic, which is something that is independent of the amount. So things like density, melting points, boiling points, and other physical properties are typically intrinsic properties. Doesn't matter how much there is. But when we're talking about enthalpy, extrinsic property, it does depend on the amount. Something else that is extrinsic would be mass. The mass depends on how much is there. The other property of enthalpy is that for a given reaction, the delta H of the reverse reaction will be equal in magnitude but opposite in sign. So I could write the decomposition of water into hydrogen gas and oxygen gas with a delta H of plus 241.5 kilojoules. I'm going to have to put some energy in order to break water into its constituent elements. I also want to point out here that you see a fraction in the chemical equation as a stoichiometric coefficient. This is okay when we're talking about thermochemical equations. Often we might be interested in the amount of heat per 1 mole of a particular reactant. And in order to get that in units of per mole, we might need to see fractional coefficients in some places. So that is appropriate when we're talking about thermochemical equations only. And the final property of enthalpy is that the delta H for the reaction will depend on the state of the reactants and products, whether it's a solid, liquid, or a gas. So in this chemical equation we have gaseous reactants and products, but if I look at the analogous reaction producing not gaseous water but liquid water, then we have a different delta H value. The delta H is minus 884 kilojoules. And the reason that it's different is because now we have to take water as a gas and release some amount of energy to get water liquid, right? And this, as we know, is an exothermic process. So delta H is going to be less than 0. And so we're going to have a more negative delta H because more energy is going to be released due to the condensation of that water vapor. So that was an introduction to thermochemical equations and how we will be looking at chemical equations and reactions in terms of their thermochemistry. Thanks for watching.